A presentation prepared by Mahzad Pakzad, designed for excellence consultant for AeroDef 2019. Materials, processes, and automation. Learning objectives. Recognize a need for organization wide support when selecting, designing, and developing automated equipment. Recognize the need for concurrent engineering in order to deliver equipment that can be managed cost effectively and produce quality. Recognize the need for identifying quality requirements and set goals for aligning supplier quality with product specifications, processes, equipment, and product control instrumentation tools from the beginning of automation programs. Automation is clarified specifications for product quality and reliability. Actually, all products need clarified specifications, but it is not unusual for people to be running operations, and every now and then you find quality people and production people arguing about what is an acceptable quality or is not. There are often gray areas for people for what is a quality, acceptable quality, and what is not acceptable quality. Now, you cannot have that when you want to design and allow automation, automated equipment to run your processes. You have to know exactly what is acceptable, what is not acceptable before you spend millions of dollars on a piece of automated equipment. So here we go. Materials consistency and their criticality must be clearly identified. Process specifications. Critical to quality, effects of the key process input variables, and controlling key process output variables. They all have to be very clearly defined. Capability and capacity requirements need to be clearly defined before capital investment. Often I go to companies, they are scrapping parts, they're rejecting parts, they wonder what is going on, and I realize that they are loading the machinery over their capacity and you're forcing some equipment to do what they're not really capable of, but people force the machinery to run those products anyway. And of course, they end up producing a lot of scraps. Extracting key factors of automation. What is automation? Materials, parts, process in sequence through a series of devices, electromechanical, optical, chemical, and others. The devices within system are integrated and controlled in a specific sequence by electronics and software to meet process needs for delivering robust output. Each device needs to serve a specific process need while working with the rest of automation system harmoniously after integration. So when we extract the keywords, key factors from the automation is there are materials, parts, process sequence, devices, system integration, controlled sequence, process needs, and robust output. So these are the key factors, the elements we need to be focusing on and studying and understanding very well when we want to design an automated equipment. We know to know the materials and parts. We need to know the process sequence. We gotta be careful in choosing the devices because not only each single device has to be able to do what it is being chosen for, but it also has to be able to work with the rest of the system. So it's not quite an independent device, independent item doing a job. It's also part of a larger system. And whatever it does, it could affect the rest of the system in many ways. And how we control the sequence, that's very important. And what are the needs for the process, what are the environment, temperature, pressure, all the characteristics requirements for the process, and the robust output, of course. Linking business requirements to automated equipment. It's very important to link business requirements to automated equipment. That way we can justify why we need to be investing so much in the automated equipment. Business as customer and product requirements are on one column, and then automated equipment design features are in the other column. First, materials variation or consistency. That will determine the handling and processing requirements for the automated equipment. So if we are not clear on all the possible variations and inconsistency of materials, whatever parts of equipment we choose for material handling could fail, because it's going to have to handle something that we didn't know, we weren't aware of when we designed the equipment. Component and assembly design. General equipment design comes based on what are the components and what are the features of components it has to handle, and what is the design of what is the assembly design. So it's basically configuration of the product determines the general equipment design. Products variations. Besides having materials variations, we could have different models, different serials of products going through same automated equipment. So we have to know where those variations, in order to identify how flexible our automated equipment needs to be, and how do we manage the flexibility, the adjustment. Operational environment and service requirements and restrictions. Equipment design support required to deliver robust output. So what is the design support for equipment? Temperature controls, any kind of sensory for pressure adjustment, vision, anything that we require to identify what the process characteristics at the moment needs to be, and to be able to manage the process requirements as it needs it to be managed. Manufacturing process steps, component specifications, and system integration. So basically, we need to have a clear understanding of what the steps, each step in the manufacturing are, and sometimes people are not very careful about determination of details on the process requirements, and missing the details may end up in the people choosing wrong components and system engineering for automated equipment. Market forecast and change. Sometimes companies change the products frequently, and they're investing a lot of money in the automated equipment, and they need that equipment to be able to handle the future product, which may be coming in a year or two. So it's good to have a chat with the marketing people to know the forecast, possible forecast, and build the system, automated system, modular for modifications just in case. Clarifying customer needs before automation. We got to make sure we understand all the new customer needs before we invest in automated processes and equipment design. All the functional requirements have to be very clear in order to clarify the requirements for the automated equipment thoroughly and accurately. So the machinery is going to be responsible for delivering what the customer needs, and it needs the designers of the equipment to need to know all the possible details, everything that is required from the product by customer. Quality demands. People need to know the quality required by the customer. What is the customer demanding quality wise? Because you can like build a Hyundai or you can build a Rolls Royce as a piece of equipment to do the job. Whether you choose a Hyundai or a Rolls Royce for your automated equipment, which one do you want it to look like? It depends on what is the quality demands, as well as what are the reliability importances. What is the importance of the reliability? Is selecting the components for the automated equipment. You can go choose a $5 uh, component, or you can choose a $50 component. Or the system engineering, what kind of electronics do you use, what kind of communication, what kind of sensory, all of that can change, it can vary depending on what is the goal, what is the reliability, what is the quality requirement. Do I need a vision? Do I need to control my temperature? Do I need to run this in vacuum? All of that has to be very, very carefully evaluated. And the robustness of output. It's finished goods. They can automated equipment can put the products together so they are like, yeah, they're together, they can function, but they're kind of clumsy. The torque is not checked, or the welds are not quite perfect welds. So how good of welding process do you want to have? How do you want to control the torque, not over torque, not under? So that all needs to be clarified very carefully before investing in the equipment. Um, these are examples of, on the top left, a specification development, process requirement evaluation by me. This is kind of like a process flow chart that has the process in sequence and also identifies all the inputs into the process, plus identifies the characteristics of each input for the process. So it's a practice. I've been doing this for 35 years, and I initiated doing this for automated equipment, actually, for evaluating requirements for automated equipment. That's why I started doing this, and I've been using it for Lean Six Sigma and all other applications as well. Under it is the left is a table showing the variations of different products going through the same automated equipment. What are the different models, and what is the differences in details? And then underneath it is a sketch of concept design for automated equipment. And to the right of it is a system design evaluation. Actually, this I did this system design evaluation on an existing automated equipment, identifying the weaknesses, why the system would go down frequently. The automated system was going down, and people were trying to troubleshoot it, and they really didn't know what they were doing, what the root cause was. So they hired me to do an evaluation of. So this I just what I should have done before I was doing after for root cause analysis. And on the top right, and the top on the bottom right, these are credits go to Ismos Engineering and Manufacturing. It's our equipment designed by them, showing automated carousel and automated line. And you see here there's a guide keeping the products lined as they go through, and then there's some optics sensing the product present. But this may need measurements, their height, their width. They may need to be adjusted for different sizes of the product, and you need to know the variation of the sizes of products and how often they have to vary it, how accurate to adjust, make the adjustments, accuracy, frequency, and all this variation need to be identified before designing the equipment, because the machine designers have a choice of doing this automatically or manually, and how they design these features depends on the application, accuracy requirement, frequency requirement, company capacity requirement to do the adjustment. So based on that, the feasibility will say, okay, you can automate, you have to fully automate this, or you can leave the changeover between model to operators. Voice of customer, system integration, process capability evaluation. So sometimes you need to be aware of the current issues with automated equipment to take it seriously. How details of product and process design evaluation you have to get involved with before designing the equipment. These are like some of the issues that people deal with after um, automation is in place, and then they realize, oops, we are having problems. We have machine downtimes, we have quality rejects, we have scraps. So some example of the voice of customers. Customer could be the production people, their customers as well. Aside customer quality issues, fit to final assembly, function, statics. The root causes could be inconsistency in output geometric dimensioning and tolerances. The way the product is put together is not within tolerance. And effects of environment on material. Sometimes material react differently to the different temperature, or difficult to process, difficult to handle materials. If the materials are difficult to handle, they're clumsy, they're floppy, and the automated equipment is not designed to manage it, and it will not deliver a robust output. And internal customer concerns, fit to assembly fixtures to the automated equipment, or function, temperature changes may cause friction between the component and the assembly tooling, assembly fixture. They can stick to the machine, they can cause all kinds of damages to the equipment. For example, mold tool damage is one of the issues. Automated equipment damage, production downtime, production capacity waste, delivery issues, and customer loyalty. If you're not delivering on time, or if you have quality issues, then you will lose customers eventually. The root causes could be failure to handle the material variation, or difficult to manage setups. The setup of the equipment is difficult. Setup people have to do very tight tolerance adjustments without a real good tooling, real good way of measuring and checking and verifying that the setup is okay. Or malfunctioning of devices could be another root cause. Devices that are not really high quality devices, they may function fine, but they malfunction frequently. Weakness in machine capability, speed, flow rate, and load acceptance, instrumentation accuracy. So if the capability of the machine, even though a machine can run, but it cannot meet the changes of the product or the speed required to meet customer demands, then they all can cause all kinds of production downtime or damage to the components. Material specifications for suppliers. When people design automated equipment, we gotta be working with the suppliers of materials that their equipment needs to handle. There's gotta be a project management activity going on, understanding what are the material requirements, and mo- a lot of times personally I go and work in between suppliers and machine designers to see what is the most cost effective choice for raw material, variation control, and automated equipment design, where the automated equipment doesn't have to be sophisticated to manage the variation. So we make a compromise in between making the automated equipment advanced and delivering consistent quality or limiting the variation. We do all of that by evaluating the bottom line cost. Companies are scared of raw material costs, so they go buy cheapest raw material, then they end up spending a lot of money on scraps. Um, the suppliers need to have a clear understanding of what specification is acceptable by the production, by the equipment. They need to have a very clear understanding of what is acceptable, what is not acceptable. And they also need to be evaluated to make sure. Sometimes suppliers make promises they cannot deliver, so and then they need to be evaluated. And one is to make sure the supplier, check for yourself, is the supplier really capable of delivering what they say or not. I personally check their equipment, I check their how advanced their operations are, how do they control it, the age of their equipment, the technology they use, and the capacity they have. And those evaluations of capability and capacity and the specifications, they need to be really approved by experts in manufacturing. You cannot just say, okay, purchasing people have checked the supplier is okay, it's approved supplier. That's not good enough. The people who are designing your tooling, people who are designing your automated equipment, they need to be looking at those materials. They need to understand how that material is managed and controlled, and they need to know those things. They need to be the judge of whether the supplier is a good supplier or not. And manufacturing capability of the supplier needs to be confirmed by the machine designers, by the tool engineers. This is an example of running design of experiment for choosing best material. For this case was automated cell, and it was also tied into an injection molding machine. So it was injection molding and automated handling of the components and assembly. And in order to identify which choice of material was the best for the application, I work between through purchasing. I work between supplier, and they were kind enough to connect me with their technical people and our own production people and process engineering. And I designed DOE, design of experiment, and we together selected a set of different materials and specified what were our objectives of the test and what we were gonna run. And actually, this ended up on the company choosing a material that helped increasing molding machine operation. The machine was often overheating, and they had quality issues when quality quite clear about what was the root cause of quality issues. It turned out that the material they were running was too difficult to melt, and we came up with substitute material that was still acceptable by the end customer and could deliver the product design requirements, but it was much easier to melt and mold. Process specifications development, understanding the science that transforms materials to end products. So when people come up with process specifications, they just sometimes go through a certain exercise for existing products or certain known knowledge, tribal knowledge for process specifications. But this is what I do as a troubleshooter. They hire me, they have quality issues, they have a new product introduced, 50% reject. They don't know why they're rejecting 50%. So I study everything for them, and this is what I do for them. I go and I understand the science that transforms the materials to end product, and that way I understand all the characteristics required to make it happen, to transform the material to end product successfully. I list the process steps in sequence. I do the process flow chart. I add all the factors influencing process. That all those factors are the characteristics required to make that process happen successfully. I identify the possible variations of that influence. Okay, if we have, like, say, temperature is an influencing factor, is that temperature going to vary? What could cause a variation of the temperature, and how, when the temperature varies, how does it affect the material property, and how does it affect the assembly structure, or how maybe I don't see effect of that property of when the temperature changes, it affects the property of material, but I might not see that in the components. um, may not show me a quality difference in the component, but when we get to the final assembly, then we see that the uh, component there is not behaving differently in the final assembly, even though as an individual independent component was okay, but in the final assembly is misbehaving. So when we check these variations and their influence on the component, we have to check everything all the way to the end of the final assembly to make sure, yeah, it's okay. We know we have got the component variation, tolerance variation within acceptable range for everything, for the process that makes the component as well as for the end product. Identifying CTQ monitoring and control requirements. How do we monitor and control the critical to quality? That is very, very important to be part of the process specification development, because sometimes that monitoring control is left to the production people and they struggle and they cannot really see it till the alarm is on, and then they try to fix it. So if we know before we have invested in equipment, we can build in the sensory required and the adjustment required to control that variation. Identifying failure modes, including wear and tear, component end of life, vibration tolerance offset, to develop practical preventive maintenance or troubleshooting guides. So once we have the equipment, now we have to worry about maintaining it, the sustainability of the equipment, and it all depends on capability of production people to set it up and to maintain it. If the machine is difficult to set up, causing people not to set up the machine correctly each time, then they can be running the machine with poor setup, offset tolerances. They can create bigger problems for the machine. This happens a lot of times with injection molding. Process specification, mixed products. So um, this is like when you have a family of products as different sizes or different features for different customers or same customer, they're all being run on a same piece of equipment. We need to map the product mixes, categorize design variations that are manufactured by the same automated system is critical, and list them in order to define process adjustments required when changing over from one product to another, the requirement for machine flexibility, selection of components, and all requirements to manage changeovers. Need to automate the adjustment or need for special guides, tooling to ensure reliable machine setup, repeatability. Possibilities of near future design changes that encourage modular equipment design. A lot of quality issues in production arise from machine setup, product changeover issues. Therefore, how the machine is designed for product changeover is very critical. Design choices for automated equipment. Successful operations and or overall equipment efficiency of automated equipment depends on the chosen components and effective systems engineering. Besides identifying the flexibility and type of automation, hard automation, fixed automation, robotics, one needs to identify the customer and production demands for quality and capacity before designing the automated equipment. Manufacturing needs to have adequate resources, training, and proper tools to control the technology used within equipment consistently. Having to make manual adjustments, making on-spot decisions that affect the output quality during changeover or machine setup could prove more expensive than automated changeover setups or using quality expensive components. So sometimes you better go with better quality and more sophisticated, more advanced automated equipment and prevent the risk of leaving critical setups to the operators. Often companies produce poor quality products or excessive scraps because they overload the equipment beyond its capacity or force it to run beyond its design capabilities. Cost of controls over dynamic environment variations could be very high if not considered in equipment design. Why is it important? Machinery may be utilizing high-tech parts and programs but not be qualified to support your specific application. So restrictions in supporting automated equipment with consistent quality input, purchase materials, parts, environment of production setup, and maintenance support are usually unique to each company and depend on organization standards. Also, some technologies may prove useless in your application when they may be working great in other applications. Companies don't usually pay for high quality materials and or expensive equipment unless somebody justifies the need to meet the expected quality and product production rates. So basically what I'm saying here is going through the exercises here to study everything in detail is important, because just because you go and spend millions of dollars on a piece of equipment, you're not getting guaranteed quality output. And the only way you can get guaranteed quality output is if you really look into the materials variations, process characteristics, define them well, and look at the product quality throughout its life cycle, not just one step of the process. And there's we can do the cost evaluation. Usually you need to do the materials cost evaluation, tooling, maintenance cost, and scrap cost, estimated scrap cost, for finding out what is the final cost for your production. Unknown caller. As I said at the beginning, organizations need to choose to use automated processes. Need to make extra effort to identify and consistently control all factors that contribute to success of operations throughout product life cycle. So today, a lot of companies are managing quality issues and production issues, supplier issues, a lot of that being managed by the people, and that's what you see in the efficiency reports or scrap reports. When you invest in an automated equipment, those issues are going to be magnified and a whole lot more expensive to manage, because the automated equipment is going to be under assumption that everything is perfectly evaluated, and not necessarily perfect, but it's completely evaluated. And the people who design the equipment know the variations and have a solution for managing it. So the equipment needs to have built-in materials management, built-in decision making, and that means that all the marketing research for product variations and sizes, different sizes, and aesthetic requirements of quality wise, all of that needs to be known. Overall design variation, standardization, quality requirements, and all of that needs to be identified upfront. And the component suppliers, the technology that you're targeting, the reliability of the technology you target for your product design, knowing that this technology is not really a reliable technology. When people handle things manually, they deal with these things, but it's going to be costing you a lot money if you are receiving bad chips, or the whole circuit board is bad, it goes bad, and then you have a monitor, you have a medical device, you have something with a bad circuit board inside of it. That's gonna cost you a lot of money. Design and development, design for excellence becomes important here. Thinking of the materials, processes, and design control choices become important, and process control in manufacturing becomes important, and more important than when you're doing it manually. And of course, change management for aftermarket design changes for future issues. These are some of the issues people deal with existing automated equipment. These are like these people didn't do a thorough evaluation of the product and customer needs when they came up with the automated equipment design. This were I was a project engineer trying to find out why the equipment was done frequently, and I was looking at it. What are the hidden product and process design features that are critical to quality? It must have been something critical to quality. People didn't know what it was, and they were not taking care of it. And what are the not measured undocumented variations of part and process assumed acceptable by current quality standards coming out of each step of the process. Why we have machine downtime, why we have devices on automated equipment that are not being used, why we have scraps, and why some are not being detected at voxel area. Why is the effect of these variations from each step uh, in the process to the next step? So what is the effect of what we build here on the next step? And what is the real cost of quality? Um, there are two situations where people want to design automated equipment. One is the process is an existing, the product is an existing product, and they want to automate the operation. So the product already exists, processes mostly they're already in place. Now, as a part of a continuous improvement, they want to automate the process. These are the things they can do to do all the studies required in order to assure a good machine delivered to them by the machine designers. Um, they need to understand market plans. Even though they're already in production, somebody needs to go back and reevaluate what are what are the new customer demands? Are they adding any new customers? What are the design changes? What are the volume, quantity requirements? What is the life expectancy of the product? And what are the quality goals? And managing supplier quality, they need to get involved with that. Understanding designers expectations for quality, getting feedback from tooling, fabrication, equipment manufacturers for transforming specifications, for design, for manufacturing, design, for assembly. So yeah, even though you already have the product and materials specified, you may have to go and change those specifications so you can handle it automatically. And working with the suppliers to run experiments for verifying and validating materials specifications, identifying risk and critical quality features, identifying requirements for practical monitoring and control of variables, and then finalizing process requirements, performing feasibility evaluation of different solutions, evaluation of process robustness, product quality, using Kepner trick methods, using Tauchi models, parameter diagram to evaluate robustness of output for each option. So basically, what I've done in the past is set up pilot runs, testing ideas, testing methods of assembly, testing materials, all different little. Sometimes do the test yourself if you can. If you cannot, find somebody who can run the test for yourself to verify. Yeah, that's a good method. And then you can allow the automated equipment manufacturers use the method for automation. The other area where the companies are uh, working on automation is when they have a totally new product. And so we're starting from scratch, from zero. We don't have the product defined yet. No, nothing is, the product specification is still work in progress. But the company plans to use high tech and automation for manufacturing. So the things they need to do can do to help the automated equipment manufacturers are define the requirements, internal customer fabrication, manufacturing, external customers function, feed, what are the requirements for making it manufacturable, for managing the manufacturing operations, measuring critical quality, key process input variables, key process output variables, identifying what they are, how to measure them, how to control them, analysis of These variations, the design of experiments to be clear what are the tolerance requirements, analysis of variations, hypnotic tree diagrams, interrelation diagrams, all kinds of analysis to identify exact tolerances required for raw materials and for the process. All kinds of analysis. This is good for both product design and automated equipment design. It can be used for both. And again, design of experiment can be used for improving the quality, um, robustness, the Tauchi model robustness, and the control for the controls, for choosing the controls, statistical process control, selection of variables, what is it that we need to control, what are the variables, what are the critical to quality input, what are the inputs that needs to be monitored, controlled, what is the output that needs to be monitored, controlled. So identifying all of this, if you're starting a product, it's a new product, there's a lot more you can do to help developing a very reliable automated equipment than you could do if you already have a process in place. Mahzad Pakzad, Design for Excellent Consultants. I started my career as an advanced manufacturing engineer, got involved with automated plant, 1 million square foot, started the assembly line automation. I realized we have a lot of issues with supplier materials. Some supplied materials were in-house manufactured, some were outside. I work with both in-house manufacturing, plastics, molding, and also work with outside suppliers for standardization and quality improvement, materials management. So we could bring the quality of materials coming to assembly lines to a point where we were able to automate the entire assembly line.